Good day. For those of you who do not know us, we're the instructional staff for EC 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to describe concatenating two linked lists. So in this topic, we will describe how to concatenate two linked lists. We will consider appropriate names for the member functions. We will walk through the steps of determining what must be done to complete this operation so as to avoid, for example, dangling pointers or memory leaks. We will implement the push front member function. We will observe that we can more easily implement the push back member function. And then we will consider what happens if we concatenate a linked list to itself. Now let's discuss pushing an entire linked list onto either the front or the back of another linked list. Because right now we can push a new node at either the front or the back. Suppose, however, we have two linked lists and we'd like to concatenate or insert one of those linked lists either entirely into the front of the other or entirely at the back of the other. Well, in this case, we could still use the same member function names. However, now we will be passing the linked list by reference. Now, the reason we're going to pass the linked list by reference and also not by constant reference is we are just going to take all of the nodes out of the argument and push them either at the front or the back of this linked list. We do not want to copy nodes. That's something we can already do with push and pop. Now we'd like to take one entire linked list and push that linked list or just relocate it at the start of another linked list. All right, so here we have two linked lists, and suppose that we want to push the linked list to the front of this linked list. All right, so this linked list has 4 nodes. The linked list has 3. So what we'd really like to happen is this linked list should start by pointing to the node containing 47, and the node containing 16 should store the address of the node containing 42. So those are the two changes we have to make. And of course, this allows us to have a single linked list following those nodes through their next pointer, and now we have a single linked list. One problem, however, is that the linked list is still storing the addresses of 2 of those nodes inside what used to be its linked list. So we're going to have to set lists head and tail pointer to be equal to the null pointer. And also we have to add the list size of the second list to this list. So now that will be 7. And let's set the list size of the other list to 0. All right. So now for this, list head points to 47, which points to 83, which points to 16, which points to 42, which points to 53, which points to 58, which points to 64, which is still the node that is pointed to by list tail, and 64 points to the null pointer. Okay, so we have just concatenated those two lists. Now the first step involves 2 assignments. We have to update the pointer to list head of this to point to the first node of the second list, and we have to point the last node of the second list to the first node of this list. Which order do we perform those in? Well, suppose that we were to update pointer to list head of this first to store the address of the other list head initially. So you may have already immediately noticed a problem. We have a memory leak because as soon as we do this, there is no way of accessing the address of node 42. Nothing is storing that address. So this says that we cannot start by assigning list head a different value. Instead, the first step we must take is update the last node of the other list to point to the first node of this list. Once we've done that, then we can update pointer to list head of this to point to the first node of the other list. All right, we've looked at the general case. However, with linked lists, there's always at least 3 cases that we need to consider under any circumstances, even if the response is going to be the same for some of them. When a list is empty, because both list head and list tail store null pointer. When the list has one node, this is slightly different because both the list head and list tail pointers store the same address. And finally, when the list has more than one node. This is the general case, and this is when both the list and tail pointers store different addresses. Thus, to determine what we should be doing, we can create the following table, even if it's only in our heads. So we will try to determine what should we do if the argument list has 0, 1, or more than 1 entries, and when this list has 0, 1, or more than 1 entries. Now, if the argument list is empty, then there's nothing to concatenate, and so we are finished. So in this case, we can just fill in all 3 entries as indicating we do nothing. It doesn't matter how many entries are in this linked list, there's nothing to do. Now, what do we do if this list is the one that is empty? Well, this is the scenario we have here. So the other list is not empty because we've already dealt with that special case previously. So really, the concatenated list is actually just going to end up being the other list. In which case, wouldn't it make sense to just swap all the member variables? If we swapped all the member variables, now this list is suddenly storing the other linked list, and the argument linked list is now the empty linked list. That's exactly what we were looking to do. Consequently, if this list is empty, it doesn't matter how many nodes are in the other list, we're just going to swap the member variables of the 2 lists. All right, what are we going to check out next? Well, let's check out the case where both the argument list and this list have 1 entry in it. Now, we already looked at the general case before, where each single list had more than 1 entry in it. So let's consider what we did there and see whether or not that applies to when each list has only 1 node in it. Well, what did we do? Well, we updated the next pointer of the last node of the argument list, and we updated the pointer to the list head of this node. Next, we set the head and tail pointers of the argument list to be the null pointer, and then we incremented the size of this list, and we set the other list to have size 0. So does this still work? Well, yes. The pointer of this list, head pointer of this list, stores the address of the first node 47, which stores as its address of the next node as being 42, which is the last node in the concatenated linked list, and that is the node that is stored in tail pointer. So in this case, there is no difference between the general case and when either linked list has only 1 node in it. Thus, if both lists are non-empty, all we do is assign the member variables as described above. so we'll call this the general case. Thus, the steps for pushing an entire linked list at the front of a given linked list are as follows. If the argument list is empty, there's nothing to do. If this list is empty, just swap the two linked lists. Otherwise, we're guaranteed that each linked list has at least one node. So the next pointer of the tail node of the argument list must be assigned the address of the first node of this list. The head pointer must be assigned to the address of the first node of the argument list. The tail pointer will remain unchanged. The size will be incremented by the argument size, and everything in the argument list must be reset as if empty. Now, question, on that last point, to reset the argument list, can we even call the clear function on that list? So that is, can we call list.clear? Well, first of all, you should realize that this is definitely not going to work. We note that if we call clear on the list, then the implementation of clear is while not empty, pop front. So the very first pop front on the argument list will delete node 47. But node 47 is being stored in this linked list's pointer to list head. So we would actually disrupt that linked list. The problem is the list argument right now is in an inconsistent state because, first of all, its nodes are intermingled with those of another linked list, and the node that is pointed to by the argument list's tail pointer no longer has a next pointer of null. Therefore, it's very unlikely anything's going to work. Indeed, what's really funny is suppose that we did call clear on the argument list. If empty was implemented as follows, where we check if the list head is equal to null pointer, then calling clear on the argument list would actually delete all 7 nodes in this linked list. That's going to delete everything. On the other hand, suppose that empty was implemented by checking if list size was 0. Well, this is going to be even weirder because now we will delete nodes 47, 83, and 16, but the rest of the linked list nodes will still be existing, although nothing will be storing addresses of them, so we've essentially got a memory leak. So basically, calling member functions on a linked list that is in an inconsistent state is likely the worst thing to do. So, unfortunately, if we actually call a member function at this point, we're probably going to be deleting linked lists deleting nodes that are supposed to be in the linked list, and thus we have a number of dangling pointers, if not also memory leaks. All right. Now, you might want to try this first yourself to see whether or not you get a similar solution in implementing what we've discussed to this point. However, assuming you've already tried it, let's carry on. Now, I'm just going to check if the argument list is not empty, then we will do something. This has the same effect of doing nothing if the argument list is empty. All right. So now we can proceed under the assumption the argument list is not empty. If this list is empty, all we're going to do is swap the two linked lists. So we'll swap all the member variables. Now the argument linked list is empty, and this linked list points to what used to be the arguments linked list. If, however, this list is not empty, we have to implement the general case we described before. So here's the alternative body, and we begin our critical code. As soon as we perform the first statement, both linked lists become inconsistent, because the first thing we do is update the last node in the argument list to point to the first node of this linked list. So now both linked lists are inconsistent. Then we update the pointer to this linked list's head node to be the address of the first node in the other linked list, in the argument linked list. Then we increment the size of this linked list by adding to it the number of nodes in the argument linked list. At this point, this linked list is more or less finished, but it's still in an inconsistent state as the last node as the other linked list is still pointing to nodes inside this linked list. So now we have to set the other linked list, the argument linked list, to appear as if empty. So we set both list head and list tail to null pointer and its size to 0. We are done. Now, pushing at the back, another member function we have to implement. However, let's reuse code if we can. Notice that pushing the other linked list at the back of this linked list is more or less the same as pushing this linked list at the front of the argument linked list. Can we use this? Can we use this to implement pushback easily? Actually, yes, we can. Let's just swap all the member variables, change the two linked lists, and then push the list argument at the front of this linked list. It's almost cheesy, but it works. Now, something that you may have immediately noted is that we just did the same operation twice. That is, in both push front and push back, we swapped all three member variables of this list and the argument list. As soon as you do something twice, you should always ask yourself, should you not author a member function that does that same operation? After all, we shouldn't ever implement the same thing twice if it is a feature that we may use more than once. There may be other member functions that want to swap two linked lists. Thus, it wouldn't be that hard to introduce a swap member function that does exactly what we've done twice already. So now the critical code is entirely within the swap function, and when the swap function returns, both lists are in a consistent state, just swapped. Now comes the important question. Should this be a private helper member function or should it be a public member function? Well, I think a user of the linked list class might be interested in swapping two linked lists. So I don't see any reason why not to make this member function public. A user who is using our linked lists may indeed want to swap two different linked lists. So I think this is quite reasonable. So we may actually make this a public member function. Also, this greatly simplifies our two previous functions. Now, if in pushing front, if this list is empty, we just swap this list and the argument list. For push back, we swap this list and the argument list, and then we push at the front the argument list, or what is now the argument list. Now, question, did we miss something critical? And this is something that's often overlooked. In fact, when I started authoring this function, I too overlooked this. Consider the following program. Here I create a linked list, and I push two objects at the front of that linked list. What happens if I try to push this linked list onto this linked list? That's not going to work because the nodes in both linked lists are the same nodes. Let's see what would happen in this particular case, and this is not going to be pretty. First of all, we update the last node in the argument list to store the address of the first node of this list. Next, we update the pointer to list head of this list, which actually doesn't change it. But then we add onto this linked list size the size of the argument linked list. Oh, we just doubled it. Then we set the argument list to be as if it is empty. So we update its list head, list tail, and list size. So now both this and the argument list are empty, and we have 4 nodes that store each other's addresses, but we have no pointers that are storing any of those addresses, and consequently, this is a memory leak. Oops. So what do we do if the user attempts to concatenate a linked list with itself? Well, we do have some options. Do we duplicate the linked list and then append it to itself? Probably not, because this is suddenly going to be a very expensive operation. Up until now, concatenating 2 linked lists can be done with a very, very small number of assignments. If all of a sudden concatenating a list requires a complete copy of that list, which may have thousands of nodes in it, that would be very unexpected behavior. Do we do nothing and just return silently, having changed nothing to the linked list? Or do we throw an invalid argument exception? Well, in this case, I suggest we actually do throw an exception, because doing nothing is almost certainly not what the user wanted. Basically, if we do nothing, don't throw an exception, the outcome is not going to give us the expected results. For example, if you were to concatenate one list with 5 nodes and another list with 5 nodes, you'd expect the one list to end up with 10 nodes, and the argument should be empty when that function returns. Well, under no circumstances can the argument be empty when the function returns if you do nothing when you try to concatenate a list with itself. Consequently, in almost all likelihood, this was a programming error. Even if it isn't, it should be up to the programmer to make an explicit copy of the linked list first, and then push that copy either to the front or the back of the given linked list. Thus, we can check as follows. Now, this is the address of the object on which push front is being called. And now we have &list. It's been a while, so perhaps you've forgotten. In a declaration, the ampersand means reference. So in the parameter declaration of the parameter list, the ampersand means that the first argument is being passed by reference. That means any interaction with the identifier list is actually going to be an interaction with the original argument. Now, inside or outside of a declaration, ampersand means take the address of. So, because list is being passed by reference, when inside the condition we check if this is equal to the address of list, we are actually checking if the address of the object this function is being called on is equal to the address of the argument. That means that we are trying to push a list onto itself, in which case we will throw an invalid argument exception with the string "you cannot push a list onto the front of itself." Good. The user can see what's going on, and the error message will help the user find the problem. Now, one interesting point, however, is that pushback calls push front. So if we try to push a list onto the back of itself, the error message is now going to be "you cannot push a list onto the front of itself." That's a bad idea because the user is going to become confused, because the user may notice that the user has never called push front. So this inconsistency is going to lead to a poor user experience. Consequently, in list back, you can either make a separate check if this equals the address of the argument passed by reference, or I'm going to show you a different way. Let's go back to try catch. So in pushback, we will swap this and list. Not a problem, because if this and the list are the same, this does nothing. However, then we will try to push the new argument list, since we've done the swap, onto the front of this list, which is now what used to be the argument. Now we will have a catch statement. If an invalid argument exception was thrown, there's only one possibility for that inside the push front member function. That is, when the user tried to push a list onto the front of itself. Well, in this case, we will simply rethrow a new exception, but this one will have a string that indicates what happened with this function call. Specifically, "you cannot push a list onto the back of itself." Now when the user sees this error message, the user will understand where to look for a problem. Following this topic, you now know how to concatenate two linked lists. And we have done this by pushing one linked list onto either the front or the back of a given linked list. You've seen how we determine the appropriate steps to take to concatenate those two linked lists to ensure that the final product is what we want and there are no dangling pointers or memory leaks. You've also observed that there are sometimes some rather interesting ways of reusing code, which was rather sort of almost elegant, if not so bizarre. You also understand that in some cases, you actually have to be very careful about performing an operation between an object and itself. And finally, you know how to avoid this issue as well by making an appropriate check before you perform the requisite operation. Here are the references, the colophon, and a disclaimer. Cheers!